All right, welcome to lesson 6-2A. So previously you were solving a differential equation sort of graphically or visually using these things called slope fields. So today we're going to look at a more analytical approach. So now we're going to be solving differential equations analytically. More specifically, today we're going to find what's called a general solution. Now, a general solution is very similar to when you were finding antiderivatives where you had that plus c, constant of integration, meaning we were finding a general form that all antiderivatives took the form of. So that's exactly what it is that we're doing here with these differential equations. We're finding what's called a general solution, meaning any possible solution would take on this general form where we just don't have a specific constant yet. So that's what it is that we're finding today. Again, this is the analytical approach, and you're going to see us use a couple of different methods, the prime one being called separation of variables. So you're going to hear me refer to that as well. All right, so we're going to dive right into some examples here. Okay, so we're going to start with this one here. So find the general solution of each differential equation. And the first one we're looking at here is y prime equals 8x to the third over y. So now, in order to solve a differential equation, in general, what we would like to do is if you have the derivative written as y prime, in general, we're going to want to rewrite that as dy dx in this case, since we can see that the other variable is an x. So I'm going to rewrite this as dy dx equals 8x to the third over y. Now, why would we want to do that? I mentioned briefly a moment ago that we're going to be using often this method called separation of variables. And the reason it's called that is we are literally going to separate the variables, meaning more specifically, we want to separate everything with a y from everything else. So now dy dx, even though we know that that is a notation for the derivative, for our purposes here, we're going to treat this just as an actual fraction where we have the quantity dy over the quantity dx. And what that means is I want to move anything containing a y to the left side because the dy is already in the numerator, and I'm going to move everything else to the right side. So that means I'm going to multiply both sides by a y. Now, you don't normally have to show me that you're going to multiply both sides by a y, but just for the sake of this example, I'm going to go ahead and show that. So I'm going to multiply both sides by a y, and that makes these y's divide out. I'm also going to multiply both sides by a dx, and that makes the dx's on the left side cancel out. And so what I'm now left with is y dy equals 8x to the third dx. So what I've done right here is I've separated my variables. So the reason we call the method I'm referring to separation of variables is because I literally separated the x's and the y's from each other. Now, this is ultimately still an equation, and just like all other equations you've ever solved, anything I do to one side, I need to do to the other. And at this point, what I'm going to do to both sides is I'm going to integrate. So now I'm going to integrate both sides with respect to whichever variable is there. And that's why we wanted to make sure that our variables matched. That if I had a dy on the left side, I wanted to make sure that I had a y here. And if I had a dx on the other side, I wanted to make sure I had an x there. All right, so now on the left side, the integral of y with respect to dy is going to just be y squared over 2. Now, normally we would have to put plus c, but because we're going to be integrating both sides, we only need the plus c on one of those sides. So I'm only going to do it on the right side. I'm going to leave the side with the y's alone. So y squared over 2 equals, now 8x to the third, again, that's going to be 8x to the fourth divided by 4, and then we're going to put the plus c for the right side. Now let's go ahead and clean this up a little bit. So I've got y squared over 2 equals 2x to the fourth plus c. Now, I'm going to multiply both sides by a 2, so I get y squared equals 4x to the fourth plus 2c. And then notice now 2c, even though c is some constant, 2c is also a constant, but it is a different constant from the first one. In other words, if this first constant were, say, a 3, well, now 2c represents 6. So it is important that we recognize that the constant that I started with is now different because I've multiplied it by 2. And even though I can leave it as a 2c, we tend not to do that. What we tend to do instead is we indicate that we now have a different constant. So I could now write this as y squared equals 4x squared, 4x to the 4th, plus, where did I get the, 4x to the 4th plus c sub 1. All right, so c sub 1, c sub anything, c sub 0, as long as you indicate that this is a different constant from the original one. That's the important thing. In fact, oftentimes what you'll see is if you anticipate that you're going to change the constant, we might even call the first one c1. And then once you multiply that by 2, we call the new constant just c. So sometimes you'll see that done as well. Okay, it doesn't really matter just as long as you're aware that these are different. Now, depending on the problem, this is an equation. So this technically right here is a general solution. However, sometimes, particularly on the AP exam, sometimes you're going to be asked to write your solution as a function, meaning specifically y equals. And so one of the things you're going to want to pay attention to is on your assignment, if the answer box starts with a y equals, so if you see y equals and then a box, then you know that you need to solve this equation for y. If you don't see a y equals, if you just see a box for your answer and it just says to write an equation, then that means it will accept any equivalent version or form of that answer. Okay, so for this one, let's go ahead and say that we're supposed to solve it for y. Well, that means I do need to take the square root of both sides. Let me do that on a separate line. So I'm going to take the square root of both sides. But remember, if I'm taking the square root while solving, I do need plus or minus. So that means we get finally y equals plus or minus the square root of 4x to the 4th plus c. And that right there is our general solution to this differential equation. And again, this was referred to as the separation of variables right here. All right, let's look at another one here. So dy dx equals 4 minus y. Okay, so once again, we're going to separate our variables. Now remember, 4 minus y, this is considered a single quantity. It's two terms, but we're going to treat that as a single quantity. So again, if I want to separate my variables, let me rewrite this. If I'm going to separate my variables, then that does mean that I'm going to have to multiply both sides by a dx. But this is a 4 minus y, and this is a dx. So I need to move this quantity to the other side. So that means I'm also going to have to divide both sides by a 4 minus y. But remember that dividing by a 4 minus y is really the same as multiplying by a 1 over 4 minus y. So I'm really multiplying both sides by 1 over 4 minus y. And so what I end up with now is 1 over 4 minus y dy equals just dx. Now technically there is a 1 in front of that dx, and you're welcome to write that 1 if that helps you. It's not necessary though. All right, so once again, now we're going to integrate both sides. Now on the left side, this is technically a tiny little u substitution. So I'm going to do that off on the side. I'm going to let u equal 4 minus y. So du equals, and you have to be careful here, this is going to be a negative 1 dy. So that means dy equals du over a negative 1, or just a negative du. So when I substitute over here, that means I now have the integral of 1 over u times a negative du. So that negative is going to come out in front. And then on the right side, with respect to x, the integral of 1 is just x, plus, I'm going to call this c1 to start with. All right, so now I'm going to go ahead and divide both sides by a negative, or multiply both sides by a negative. So now I have the integral of 1 over u du equals, now this is going to be negative x, remember, plus a negative c1, which is now going to just be my new constant c. Again, it's just the opposite sign, but it is technically a different constant. If this first one was positive 2, this is now a negative 2. All right, so, and yes, you could also make this a minus, but again, typically you want to write this as plus the constant. Okay. All right, so now the integral of 1 over u, of course, is going to be the natural log of the absolute value of u equals negative x plus this constant here. And again, thinking ahead, you wouldn't necessarily know this yet, but I'm going to go ahead and call this constant right here constant 2, because it's actually going to change one more time in just a moment. All right, and then don't forget, we're going to substitute the u back in with a 4 minus y. So I have the natural log of the absolute value of 4 minus y equals negative x plus constant sub 2. All right, so now, again, this is technically an equation, but if the answer box says y equals a box, we need to solve this for y. Now, how do we get the y by itself when it's inside the natural log? And the answer is we're actually going to raise both sides of the equal sign as a power of e. So really I have e to this power equals e to this power. Now the reason that we do that, think about what happens now. So e and natural log, if you don't recall, those are inverses. They cancel each other out. So we're just left then with the absolute value of 4 minus y. Now on the right side, we have e to the negative x plus c sub 2. Now you might recall from your exponent rules that if I have a to the m times a to the n, that equals a to the m plus n. It's the sum of the powers. And that's exactly what's happening right here. These two exponents are being added together. So I could break this apart into e to the negative x times e to the c sub 2. All right, so again, that's based on this exponent rule right here. And the reason we do that is e to the c sub 2, that's just another constant. Again, it's a third type of a constant in this problem. Remember, we had this initial constant, and then we took the opposite of it, and that turned it into a different constant. And now we're making that the power on e, which makes it a third constant. And that's the one that I'm just going to call c. So now I have the absolute value of 4 minus y equals c times e to the negative x. Now, that absolute value, that's a little bit trickier. Just kind of go with me on this. The absolute value bars, remember, all that this means is that whatever's inside is going to give us the positive, a positive value. So because that constant right here could already be positive or negative, that sort of absorbs the absolute value here. So we can now just turn this into 4 minus y equals c e to the negative x. And then finally I can subtract the 4 from both sides. And then finally I can divide by a negative 1 or multiply by a negative 1. And I get y equals 4 minus c e to the negative x. All right, so that one showed you a trick that you will end up using probably more often than you would care to. And that was this trick right here, where I went from e to this power, and I ended up splitting that up so that I can get this new constant. So you're going to see that trick get used pretty often when solving differential equations. All right, let's do another one. All right, what about a differential equation that looks like this one? So we have 2 plus x to the fourth y prime minus 8x cubed y equals 0. So there's quite a bit of stuff going on here. First of all, we've got that y prime that we know we're going to turn into a dy dx, but before we even get there, we've got to deal with the fact that we actually have a couple of different terms here. So because this right here is my y prime and this term right here doesn't contain any derivatives, I'm going to move this term to the other side first. So we're going to add the 8x cubed y to the other side. So that's going to give me 2 plus x to the fourth dy dx equals 8x cubed y. All right, so now we can do our separation of variables. Now I know that I need to get this y to the other side to be with its y. I need to get the 2 plus 4x to the right side as well as the dx. Okay, so I've got three things that I need to move. So first, let's go ahead and multiply both sides by a 1 over y. We're going to multiply both sides by a dx. Actually, before I do the dx, we're going to multiply both sides by a 1 over 2 plus x to the fourth. And we're going to multiply both sides by a dx. All right, so now that's going to give me 1 over y dy equals, now over here the y's are gone, that's going to give me 8x to the third over 2 plus x to the fourth dx. So now we've separated our variables, and so now we can integrate. Now the left side is going to be nice and simple. That's just going to become the natural log of the absolute value of y. But on the right side, this is definitely going to need a substitution. I notice that the power in the denominator is 1 degree higher than the numerator, so I'm going to let u equal my denominator here. So u equals 2 plus x to the fourth. That would make my du become 4x to the third dx, or in other words, dx becomes du over 4x cubed. So this integral now becomes the integral of, I have 8x to the third over u times du over 4x to the third. So the 4x to the third divides with the 8x to the third, leaves me with a 2. So that means now I have the natural log of the absolute value of y equals 2 times the integral of 1 over u du. So let's go ahead and integrate that side now. So now I have 2 times the natural log of the absolute value of u, which remember is 2 plus x to the fourth, plus my new constant here, or my first constant actually. All right, so now, before I go on, no, you know what, I'll do this first. So now we're going to go ahead and do what we already expect. I'm going to raise both sides as a power of e. So that means on the left side, we just get the absolute value of y equals. Now on this side, again, e to the c sub 1, that's going to be some new constant that I'm going to just call c, times. Now here I have e to the 2 natural log of 2 plus x to the fourth. I'm going to use my exponent rules and move that 2 up as a power on the argument. So this is really e to the natural log of 2 plus x to the fourth to the second power. Now, a couple things here. 2 plus x to the fourth is always going to be positive, so I actually didn't even need the absolute value bars here. But regardless, now I can actually cancel the e and the natural log. I couldn't do that before because of that 2. I had to move that 2 up as my exponent. Okay, so now I get the absolute value of y equals c times 2 plus x to the fourth squared. And again, I got rid of the absolute value here because this is always positive anyway. And then finally, because that constant could be positive or negative, those absolute value bars on the y can sort of quietly go away. And this is our general solution. All right, let's just do one more here. So we've got the square root of 1 plus x squared, y prime equals x. So again, first thing I'm going to do is rewrite that y prime And then now we can separate our variables. So notice the only thing we have with a y in it is the dy. Everything else we're going to move to the other side. So that means I'm going to be multiplying by a dx and dividing or multiplying by a 1 over square root of 1 plus x squared. So that means I've got dy equals x over the square root of 1 plus x squared dx. So now I can go ahead and integrate both sides. And again, if you'd like to squeeze a 1 in there in front of the dy, you are welcome to do that. It's unnecessary, but it might be helpful to you. So on the left side, that now just becomes, remember the antiderivative of 1 with respect to y is y. Now, on the right side, we're going to go ahead and let u equal the integrand, so 1 plus x squared. So that would make du become 2x dx, or in other words, dx becomes du over 2x. So our integral now becomes, we have x over u to the 1/2, and then we get du over 2x. So I'm going to move that 1/2 out in front, and I get y equals 1/2 times the integral of u to the negative 1/2 du. All right, so now we can finally integrate, and we get y equals 1/2 times, so this is going to become u to the 1/2 divided by 1/2 plus c. Those 1/2s actually cancel each other out, and I get y equals, I'm going to go ahead and replace the u again, so I get the square root of 1 plus x squared plus c. All right, so again, this is referred to as separation of variables when we move everything with an x to one side, everything with a y to the other side. And we are finding general solutions. Again, that means your answer will still have this unknown constant value in it. Okay, now again, my last tip is when you are doing your separation of variables, if you have a situation that looks like this, where you have something like dy over dx equals 8y over 3x. As you are separating, it's going to feel really tempting to feel like you should multiply both sides by a 1 over 8y, because you see that 8 sitting next to the y. But I'm telling you right now that you're actually much better off letting constants stay where they are on the x side if possible. So if you're just multiplying 8 with a y, there is no reason to move the 8. You are much better off leaving the 8 with the right side and just multiplying by a 1 over y. Because then you end up with a 1 over y dy equals 8/3 times 1 over x dx. And that's going to be much easier to work with as opposed to dealing with an extra constant on the left side. And again, because remember, oftentimes you're going to be solving for y. So the less stuff you have on the left side of this equation, the better off you are. And then my final comment is, remember, it doesn't have to just be x's and y's. As you'll see in 1 or 2 examples or problems in your assignment, it might be something like, dx dt, or it could be dr ds. Don't let that throw you off. Just remember, whatever variable you have in the top, that's going to have to be on the left side. Whatever variable you have on the bottom, you're going to want that on the other side. Okay? All right, good luck.